All right. Hi, folks. My name is Sunny, and I'm here with my colleague Raja, and we are product managers on Google Kubernetes Engine on Google Cloud. Thanks for joining us tonight. Let's get started. So Kubernetes, I think you all are aware of what it is. It is the open source de facto orchestrator for containers, right? Very popular, hardened for production. It's known for its reliability, its scalability, and so forth. And then Ray, the reason why we're all here for, is another open source standard, very popular with data scientists and AI ML engineers, known for its Pythonic nature, for its rich libraries, and so forth. So when you have these two open source popular standards together, what it creates is a powerful distributed OS for AI/ML, a singular elastic platform for you to build and deploy AI/ML workloads. And what we're doing at Google Cloud with AnyScale is partnering with them in a technical partnership to really make Ray and Kubernetes be more aware of each other and bring more integration so that we can bring you more enhanced observability, scalability, and performance across day 0 to day 2. So Raja will walk us through that.
Thanks, Sunny. All right, let's get into this a little bit. So, I think what we've seen a lot of is that there is a thing floating on my screen. There you go. I think we've seen a lot of the customers that we've seen adopting Ray at Google Cloud have been doing that on Kubernetes. It's their standard, but also it allows them to have a nice flexibility of the workloads and get better quota handling and resource orchestration, et cetera. But when they start building this out, I think one of the things that they really think about is across 3 different stages of that life cycle. How do they enable and deliver a nice, seamless developer experience to their users? How do they then get performance and scale as they get into day 1 and the workloads grow? And then later on, as problems arise, et cetera, how do they address troubleshooting, observability, as well as other lifecycle things that happen as well? And as they think about the challenges that they face in each of these areas, as they start through day 0, a lot of it comes down to just making sure that they have resilient and performant platform at the scale that they need to. Some of them are, 1,000 node clusters. Some of them go all the way up to 50, 60,000 plus node clusters as well. But they also need to have some topology awareness for scheduling for low latency performance. They need to have choices for how they kind of layer in rather abstract away some of the resource orchestration that happens for the different workload types through the different, as they go from training and inference and pre-processing, et cetera. And then having a nice way to kind of integrate back in Ray so that you're able to perform in an optimal fashion, taking advantage of those capabilities on the Kubernetes side of things. And then when they start getting past that day 0, they need to start addressing problems around inefficient resource consumption and utilization, minimizing disruptions. They need to start saving, really, it's at the end of the day, and getting better price performance. Node startup times become important for them as well. And then how do they kind of distribute them as they grow? And then when they get into day 2, one of the challenges we heard a lot about is that challenge with correlation. Let's see that a job didn't execute, nothing in the Ray event logs. Go down to the Kubernetes, it's hard to correlate to understand how one impacts the other. And then over time, as we heard just a little bit on the Datadog side, lost logs, past execution of jobs that took place, how do they know and tie that back to what happened and troubleshoot? So we're going to talk a little bit about that and how we actually kind of start focusing on these bits. When we start from the day 0 part of this, it all comes down to enabling and delivering a performant and scalable platform. Kubernetes is a great place to start with that, with some advanced scheduling options, including support for DRA now. And then layering in advanced technologies around RDMA for better networking and other aspects too. KubeRay is really the piece that brings everything together, bringing you visibility from the Kubernetes parts back up into Ray. It's that easy button to kind of start automating that awareness of each other, and it starts facilitating things around auto scaling and the monitoring observability and the lifecycle handling too. Resource efficiency. Oftentimes customers have custom schedulers that they layer in on top. If not, there's open source options as well. When you start thinking about multiple teams coming onto these clusters, resource quotas, how you provision those out, how you do priority handling, all of those types of things, preemption handling becomes important. So making sure you have a solution or a platform that takes advantage or provides all of that. And then a diverse choice of accelerators as well. We found that different types of chipset are better for different types of workload types. We've seen a growing need for additional choices beyond just the NVIDIA GPU chipset. So TPUs obviously on Google Cloud are supported. We've actually brought some of that back into the Ray side and making that better and more useful. As we start going down into this a little bit deeper, I think when we're talking to customers, KubeRay is something that we usually start part of that conversation with, because when you start thinking about deploying this on top of Kubernetes, you want this to kind of be able to scale in the same way you think about scaling those resources, scaling your clusters, making sure that everything is wiring together the way that it has to. And KubeRay is really at the core of that by initially starting with like just mapping through those Ray objects to Kubernetes CRDs, Ray cluster, RayJob, Ray service. This is what we leverage to facilitate things like label-based scheduling now, which is supported. And that becomes important when you think about like in-place pod resizing and auto-scaling as well. For that to be really effective, you've got to use label-based scheduling. You then therefore have to have KubeRay so that awareness of the nodes, the labels, et cetera, pass all the way through. Fault tolerance, it'll handle some of those dead Ray nodes. And so as you think about deploying those clusters on top of it and being able to like make sure that the Ray head nodes are in HA, fault tolerance, if they get scaled up and they get replaced when there's an issue, KubeRay facilitates all of those bits and then provides that observability hook along the way, so you can like fine tune and troubleshoot and find out what's going on, that correlation. We'll talk a little bit more about some of these in just a bit. On Google Cloud, we do try to make that a little bit easier for you. So we do have a managed Ray add-on. I think what the key things is that it reduces some of those operational overhead. So one, we'll lifecycle that for you, but we'll also automate the integration. So all those things that we talked about happens kind of out of the box. So we'll wire it back through either into our cloud monitoring stack. We'll do the correlation of the log, pulling down the Ray events, tying that back to Kubernetes events. So when you go into the console, you can see all of that in one area. And so all of those things are supported along the way. Some of the things that we've done is really invested a lot in the infrastructure. Performance matters. That topology awareness matters too. DRA provides some of that, and KubeRay it does enable or facilitate some of those things. But on GKE, when you go to deploying a cluster, we'll automatically deploy those clusters or your resources in a low latency manner, rail aligned, nodes as close to each other as possible so you get the best performance, and RDMA, so really increasing that throughput of communication from node to node. We've also done some things, there's a number of technologies out there, and methodologies rather, leveraging other boot disks to get speed up loading times, streaming those images, et cetera. We kind of facilitate handling all of that out of the box and providing in hooks to support things like our managed cluster or other things, so that you really reduce the time and the cost. When you start getting to larger scale, you start getting to cases where like the actual resource consumption, et cetera, can matter. So those minutes per node matter. We reduce that down, bringing it to less than a minute to actually boot up some of those nodes, saving a tremendous amount of cost. Integrating that observability matters as well. So we've wired those things up. There's also the option you can tie it back to your own stack for observability. And then all that gets tied back into like the overall GCP ecosystem in the UI. All the things for identity handling, security, et cetera, all of that flows through as well. And the KubeRay add-on that we have just facilitates and makes that a lot easier. Q is something that's kind of interesting and it's important, because when we start thinking about job handling on top of Kubernetes, very often the workloads that are running on there, and to optimize and take advantage of all of it, can be a mixed bag. On the Ray side, it does a great job of job handling and execution, et cetera. But sitting in front of that with Q, you can handle tenancy management to optimize it, to set quotas, handle challenges with making sure that you're leveraging like the hierarchy of like fair sharing and then borrowing, and then priority-based placement. So if you've got Ray jobs in there and Ray clusters and you've got secondary workloads on there as well, you can take advantage of all of that. So that brings all of that together. And then for gang scheduling even, Q on the front end of it can facilitate that coming through to the different Ray clusters, ties in even with compute classes that we have to do fallback. So as you're scaling up at that same time, the GPU or the accelerator is not available, we'll fail back to a secondary option. So the job executes no matter what. All that kind of comes together to like a nice, great experience as you start bringing on multiple teams and scaling up. All right, with that, I'm going to hand it off to Sunny to go a little bit into performance and scale.
We can find a way to the stage. So performance and scale becomes unnegotiable as you enter into day one, right? And it's expected to intensify. I mean, what we're seeing is probably around 35x the model size growing every 18 months, which is an explosive growth. But you couple that with an astounding fact that around 70% of the organizations, they spend less than 70% of their expensive compute. So there's lots of things going to waste here. So how do we address that? Let's start with in-place pod resizing, IPPR. You may be aware, Ray Autoscaler V1, it's a horizontal scaling model, right? So when it's run on Kubernetes, it does some funky things. So when you request for even maybe a small resource request, what it might do is actually spin up a new Kubernetes pod, maybe even a Kubernetes node, which takes minutes. And these are minutes that you don't have when you're running a time-sensitive, very bursty workloads. What IPPR does is it prioritizes vertical scaling. So to a node that it's already running, you don't even need to stop the work node and then restart a new one. Onto the running pod, you can add CPUs and memory requests to vertically scale and thereby reducing OOMs that you might experience. The other piece of this is that because it's deeply integrated with Kubernetes, you can use Kubernetes events to get a little bit closer observability as well as debuggability into what's going on with the scheduling logic that remains a black box with horizontal scaling, right? Another sort of bottleneck that we see in day one frequently is around startup time, right? Many of us are pulling large container images, ML models, and data sets and so forth, so it takes a little while for startup. How we address this is with secondary boot disk and image streaming. So secondary boot disk, make sure that you can preload your data sets so your Ray workers can experience it as sort of a local data as they start at the time of provisioning. And then image streaming, what it does is that your container can start without having the entire container image loaded on. You can intelligently pull sort of parts of that image and get it going while the rest of it is running in the background. So this reduces your startup from minutes to seconds. This powered with GCS Fuse, Hyperdisk ML, very performance storage options. Hyperdisk ML in particular can pull 12.9 gigabytes per second per instance, which means your GPUs are well fed, they never go starving, and it gives you option to enhance your model checkpoint. And all this embedded on Titanium ML networking, sort of a highway for your data that would freeze up your CPU resourcing, as well as allows you to do more enhanced distributed training as well as data transfer. All this on GKE is meaningfully performant, so you can see 80% lower startup time, 2x faster node readiness, and 20% less idle capacity. This real quick, label-based scheduling is important here, especially in the times that we live in with GPU shortage. What you're seeing on the left is essentially ML engineers and data scientists. They can do this in Ray. They don't have to touch an YAML file. They can use Python to sort of narrate the fallback strategies from H100s, fall back to H100 on demand, and then go to L4. So you can have a cost-aware fashion of how you distribute your accelerators, and all while platform admins retaining their granular control over Kubernetes. And lastly, if we're talking about performance, we have to talk about AnyScale runtime. The graph that you see here is AnyScale runtime running on GKE for batch inference workloads. It's 44% faster than running on OSS Ray. So for some of your most demanding AI workloads, this integrated platform is really the recommended fashion to run your AI workloads for. So with that, I'll pass it back to Raja for day 2.
And we'll just a couple slides real quickly. When we talk about day 2, a lot of it just comes down to how do you start correlating? You've got the developer, you've got your platform admin, so you can plug this into your stack using KubeRay, tie it back to Prometheus, Grafana. But how do you find out what's happening where? There's loss logs and metrics, there's correlation challenges. As mentioned, we've got that unified view that brings it all together in one spot, all the logs, all the metrics, etc. We're also piping through TPU metrics into Ray Console now, so if you're leveraging that. But at least on GKE, we can do that correlation for you out of the box. You've got to put that stack together otherwise. But we're starting to do more to make it easier and continue to advance that going forward. And the last thing, we talked a little bit about this, the Ray history server. When jobs end and finish, you lose all the context, the data, what happened, where was that taking place, et cetera. Especially as you can look through on the Kubernetes side, but if you don't have that context, what was happening, it's not there. One of the things that we're exploring and working with AnyScale on is a concept that we're calling the Ray history server, which maintains that persistent information about the jobs, what executed, where it was, the details, and it manages some of that for you so you can do that long-term troubleshooting, optimization, and investigation. If you want to hear any more about what we have, we're over at P2 over in the front side, and looking forward to hearing from all of you. Thanks so much.